Let's take a look at section 6.4, the wonderful world of circles and ellipses. Now, again, I'm hoping you know a thing or two about circles. We'll talk about writing the equation of a circle in standard form, and then we'll talk about similarities, differences, definition of what an ellipse is, and why do we even care about these things. Standard form of the equation of the circle. Now, hopefully, again, you're already familiar with the unit circle. Again, a circle centered at 0, 0 with a radius of 1 unit long, whatever that is. So now we're going to look at transforming that basic unit circle and move the center anywhere and change the radius to anything. Suppose you're given this as the equation of a circle. X plus 6, the quantity squared, plus y minus 4, the quantity squared, is equal to 1/4. How is it similar to, how is it different from our basic unit circle equation? Well, clearly, we've moved the center from 0, 0. Now, careful. Let's go back here. It says x minus h and y minus k. So when we get an equation here where it says x plus 6, what number subtracted from x would give us positive 6? It has to be negative 6. Okay, so that'll be x minus negative 6. So our x coordinate there is negative. The y coordinate is positive. Okay, so this circle has been moved 6 spaces to the left, 4 spaces up. What happened to that radius? Again, the 1/4 from our basic formula we saw on the last page. 1/4 is r squared. Take the square root of that. Square root of 1 is 1. Square root of 4 is 2. Again, take the positive because we're talking about radius. We're talking about distance. Distances can never be negative. So the radius is 1/2. So we can simply say the unit circle has been dilated by a scale factor of 1/2. Okay, for an ellipse, it's a stretched out circle where the distance from the center isn't the same in every single direction like it is with a circle. It's the set of all points in a plane where the distance from two really, really important points have a constant sum. Those points are called focus 1 and focus 2, or yay, Latin, foci. We should be able to put a line through both foci. We call that the focal axis. Um, the midpoint of that is going to be the center of the ellipse. And then we're going to find vertices on the ellipse. Okay. So here's an example of an ellipse where the focal axis is horizontal. So again, we're going to find that center point. We're going to find vertex points that are actually on the ellipse, but we also need to find coordinates for each focus point. You'll notice here, huge difference. Um, we have fractions. Yeah, suck it up and deal with it. Another huge difference with the standard factored form of a circle, it's set equal to r squared. I mean, whatever the square of the radius is, here for an ellipse, we're always going to take the equation. We're going to do some division and make sure it's set equal to 1 every single time. Now again, as I kind of warned you, the first one here, if the focal axis is horizontal, that's what we're talking about with the first one. Again, this first column here. So the vertices are going to be, again, take a look here, denominator of the fraction, take the square root, plus or minus. So half of our major axis is going to have a length of A. The minor axis is, there we go, going to be B. How are we going to find the foci? Dear old Pythagoras. Now again, it's kind of tricky. It's not a squared plus b squared equals c squared. It's the relationship between these numbers in our denominators that are going to give us the focal length. And then if it's more like this, where the y-axis is going to be the focal axis, it's going to be longer than it is wide. Again, notice here for the foci and those vertices, we could easily find, we flip that around. So again, if it's on the y-axis, then the x-coordinate is 0. Now a squared is equal to b squared plus c squared. Why does that work? Again, we defined the curve itself. It's the sum of this and this is constant. So if we go from here to there and here, the sum of those segments is the same. And again, where the major axis is horizontal or the major axis is vertical. So here's an equation. Now we should be able to identify that this is the equation of an ellipse by virtue of the fact that x squared and y squared have different coefficients. If they're the same exact value, it's going to be a circle. Because they're different, this is an ellipse. Now, that and the fact that the directions say it's an ellipse. So again, standard equation for an ellipse, we divide everything, we set it equal to 1. So in this case, we're going to divide everything by 36. So 9 over 36 will reduce down to 1 over 4. 4 over 36 will reduce down to 1 over 9. And you'll notice, again, they had mercy on you. Hey, this is a perfect square. That's a perfect square. Doing these calculations shouldn't be all that tough. Notice, again, the bigger numbers underneath the y. So the focal axis is the y-axis in this case. 9 minus 4 is 5. C squared is equal to 5. Again, you're just going to always take the bigger number minus the smaller number, and then we're going to take the square root to find the value for C. Okay, so our vertices are going to be at 0, 3, and 0, negative 3. The foci are going to be at 0, square root of 5, and 0, negative square root of 5. And again, the value for C is going to be less than that distance to the vertices, because we're always going to be subtracting, we're going to take the difference between the denominators. So square root of 5, decimal approximation about 2.236. So the foci will be inside the ellipse. Okay, so here's, give you the equation. Let's figure out some where the center, focal points, vertices. Let's go the other way. They tell you find the equation of an ellipse where the foci are at -2, 0 and +2, 0. The minor axis has a length of 2. That's all the information that we need to write the equation. Now again, because think about sketching a graph, or mentally at the very least. -2, 0 and +2, 0. The center of it has to be exactly in between. Well, that means the center's at the origin in this case. Again, and these are the foci. Sorry, 1 and 2, 2 and 1, who cares? Order doesn't matter really much there. So our value for C is equal to 2. They tell us the minor axis, the whole thing has a length of 2. So that means, okay, for our minor axis has to be the y, because the foci are on the x-axis. If they're telling us the minor axis has an entire length of 2, that means, well, the value for B is only going to be 1. We know that C is 2. We know that B is 1. With our lovely equation here, we can figure out that A squared, 1 squared is 1, 2 squared is 4, 4 plus 1 is 5, A squared is 5. Now again, I really don't care what A is at this point in time. They wanted the equation. So again, here's A squared, and here's B squared. It's an ellipse, so the equation should be set equal to 1. There we have it. Suppose we move the ellipse. Suppose it's not centered at the origin. Well, we're going to do the same x minus h, y minus k that we just looked at for circles. But again, it's going to be in standard form, so that means it's going to be equal to 1. Okay, so some lovely examples here. So centered at HK. We're going to go a distance of C to get to one foci in this direction, and -C to get to the focus on the other side. We're going to go a distance of A to get to the one vertex, -A to get to the other vertex on the axis, major axis. And again, that major axis might be horizontal, that major axis might be vertical. All right, let's look at this description here. Find the standard form for the equation of an ellipse where the minor axis has endpoints of -1, 4 and 5, 4, where the major axis has a length of 8. So again, if you could at least mentally sketch that out. If we're looking at the minor axis, going from -1, 4, that's on the ellipse, and +5, 4, that's a distance of 6 spaces total. The major axis got to be bigger than 6. In this case, it's 8. So if we plot the points that they're telling us here, okay, so negative 1, 4 to the left, positive 5, 4 to the right. So that gives us a total distance here of 6, which means this length is 3 and that length is 3. If they're telling us the major axis has a length of 8, that means 4 spaces this way, 4 spaces that way. The center has to be exactly halfway in between these endpoints that they gave us. So we should be able to say that the center is at the point 2, 4. Okay, try and keep all that in mind. Centered at 2, 4. The major axis has a length of 8. So our value there for B has got to be 4. And if A is 3 and B is 4, we can write the equation. So again, A is 3, 3 squared. We're going to put 9 as our denominator under the x variable. B is 4, square that, 16 becomes the denominator under our y variable. And again, we figured this out on the previous one. The center is at 2, 4. Remember to change the signs. I think they missed a wonderful opportunity here to force you into finding where the foci are located with, the 3, 4, 5 right triangle, but that's all right. Suppose you're given the equation. Again, going back and forth here. Where's the center? Where are the vertices? Where are the foci? So standard form, compare that. So the center here, again, so again, the thing to keep in mind here, you should notice almost immediately, is the fact that, yes, we have a larger denominator under the y variable. So in this case, we're saying that 9 is a squared, which means a is 3. And again, from the x here, it's always x minus h. X minus negative 1 is how we get x plus 1 from our equation. So the center is at negative 1, 1. Again, we're always going to use the larger denominator there as our value of a squared. So a is 3. So our vertices, again, h is going to stay the same because, again, this is going to be, the major axis is going to be vertical. So we're going to take 1 plus 3. So that'll put us at negative 1, 4 as one vertex. And then k minus a. So 1 minus 3 puts us at negative 1, negative 2 as our other vertex on the major axis. And again, we'll take a squared minus b squared. 9 minus 4 is 5. Take the square root. C is square root of 5. Oh, that's going to be messy. Our foci will be at the same exact thing that we just did for the vertices, but now instead of adding a, we'll do plus or minus c. So 1 plus square root of 5 puts us at about 3.24. 1 minus the square root of 5 should put us at approximately 1.24, negative 1.24. Now again, directions just say find the center, check, find the vertices, there they are, and find the coordinates of the foci. They're not asking you to graph it at this point because, yeah, you know how to plot points. Suppose they want to challenge you to take an equation and put it in standard form. Okay, now again, I'm looking at the fact that the coefficient of x squared is implied to be a 1. The coefficient on y squared is not 1, it's 4. This has to be an ellipse. We'll come back to that and do some more review later. So our challenge here is to put it in standard form. So that's why we started with the completing the square method back in chapter 0. This time, oh joy, we get to do it twice. We're going to do the completing the square method once for the x variables and then again for the y variables. Okay, so yeah, in this case, math, one of the few places where we can say segregation is going to be our first step here. We're going to put together the x squared and the x term, leave a space. We're going to write the y squared adjacent to the, well, in this case, negative 16y, leave a space. And we're going to move that constant to the other side. Now again, this should look somewhat familiar to what we talked about in chapter 0, but now we're just doing it twice. Big deal. Okay, again, half squared added to both sides. So in this case, half of 2 will give us 1. 1 squared is 1, so we'll add 1 here and we'll add 1 there. Now the y's are just a little bit trickier here. The fact that we have the 4. This is what makes the difference here with completing the square for a circle different than completing the square for an ellipse. The fact that we have that 4 as the coefficient on the y squared, we've got to factor first. 16 divided by 4 will give us negative 4. Half of negative 4 will be negative 2. We'll take negative 2 and square it. And we're going to add 4 to turn it into the perfect square. But then we have to redistribute. That's why we're adding 16 to both sides. So again, it's got to be factored down. That's why I'm not just taking half of the negative 16, which would be negative 8, and square that and not adding 64 to both sides. We need to factor it to make it into this perfect square trinomial where the y squared term has a coefficient of 1. So we can factor it down into this. That's why we did the completing the square thing in the first place. And negative 13 plus 1 will give us negative 12. Negative 12 plus 16 is positive 4. Hold on, it's an ellipse. We need to make sure that we get it set equal to 1, so we're going to divide everything by 4. Here we go. X plus 1 squared over 4 plus the quantity y minus 2 over 1 equals 1. So the center of this ellipse will be at, again, change the signs. Negative 1, 2. The major axis is horizontal because, again, the denominator under the x is bigger than the denominator under the y. A squared is 4. So that means a is 2 for the major axis. Square root of 1 is 1, so the minor axis is 1. let's try it for a circle. Now again, you'll notice the coefficients of the squared terms are the same. That's how we know this is going to be a circle. Same thing as before. Put the x squared and x term together, leave a space. Put the y squared and the y to the first terms together, leave a space. Move the constant to the other side. Now, because the coefficients for both x squared and y squared are 1, then we're back to, again, things we saw in chapter 0. Half of -10 would be -5. -5 squared is 25. Add 25 to both sides. Take a look at the y to the first term. The coefficient is 6. Half of 6 is 3. 3 squared is 9. Add 9 to both sides. So in its factored form, we get x minus 5, the quantity squared, plus y plus 3, the quantity squared, equals, okay, 2 plus 25 plus 9 is 36. Now again, careful, don't go overboard. This is a circle. We are not going to divide everything. We're not going to set it equal to 1. The center is at 5, -3. The radius is 6. Now, again, this definition of an ellipse, how an ellipse is actually formed, ellipses make wonderful reflectors. If you consider light to be particles, they can bounce off, or you consider them waves like sound is. As we looked at last section with the parabola, we take that thing focal axis, okay, we understand where the foci are, and use that as an axis of rotation, turn it into a three-dimensional object, we get an ellipsoid. If we put the source of a signal at one focal point, it will always reflect off and go to the other focal point. Example 12, the lithotripter. Yeah, if you're not familiar with this, I looked it up. Using ultrasonic waves, blasting them through the soft tissue of a person who has kidney stones. Okay, so those are deposits of usually calcium that build up in your kidneys and can block things, and they get too big. Yes, they become very, very painful, especially if your body tries to expel it. Think about how your body filters things through your kidneys, and then how it then eventually exits your body. So a lithotripter will aim ultrasonic pulses at that kidney stone and break it up into itty bitty little pieces that should be easier to expel. So it's set up so that it will focus these ultrasonic pulses here and bounce them around because it's an ellipsoid that's has a generator at one focal point, and they know exactly where to aim it for the other one. So suppose that our ellipsoid here for this machine has a major axis where the endpoints are at -8, 0 and +8, 0. One of the endpoints of the minor axis is at 0, 3.5, where are the foci? Okay, so we know our value here for A, because they said major axis, going from -8 to +8 is a total of 16 spaces. Divide by 2, A equals 8. Again, from 0 to 3.5, that's our value for B, 3.5. So if we take 8 squared minus 3.5 squared, take the square root, our distance there for C is approximately 7.1937, blah, blah, blah. So the foci have to be at negative 7.19370 and positive 7.19370. Solved a lot of problems with astronomy once we figured out that planets orbit around the sun in a path of an ellipse, not a circle. It was a major controversy at the time. The astronomers could never reconcile and had to do, oh my goodness, really complicated, convoluted calculations because they thought, I'm sorry, I can say this here in hindsight, their own arrogance, their own opinions of what the universe is like. Oh, it was perfectly created by the God of Genesis. And by perfect, we mean everything is circular. Why does a circle mean perfect? The ellipses are perfectly symmetric. They're wonderfully useful. To just say that, oh, it has to be a circle was a false assumption on their part. The Earth actually orbits around the sun where the sun is at one of the foci. Perihelion, close to the sun. Again, the way, if you've never studied astronomy, you're not paying attention to the interesting things about the Earth here. Perihelion, now this picture is very, very distorted. Um, the major axis and the minor axis for the Earth's orbit around the sun are not nearly this different here. They're, again, in astronomical terms, they're not that far off. Perihelion, when we're actually closest to the sun, actually happens in December. Wait a minute, we're closest to the sun, it's really cold. That's because of the tilt of our axis. We're tilted away from the sun. So, yeah, things actually heat up in the southern hemisphere in December more than things heat up in the northern hemisphere in July. And again, we could go through all of the theological ramifications of that. Um, the vast majority of the land mass is in the northern hemisphere. Was this done intentionally? So we come to something that's called eccentricity of an ellipse. What's the ratio here of how distorted is it? Okay. Again, A is going to be the length of the semi-major axis, B is the length of the semi-minor axis, and we're going to do the same thing that we did before, that C is equal to, take A squared minus B squared, take the square root, and that's C. Then divided by the value of A is what we use as the ratio for eccentricity. Okay. So again, that's a word with which you should become familiar. Okay. Now again, with this, not an accurate picture here at all. This is really emphasizing the fact that the sun is at one focal point. The orbiting object, such as, say, Earth, comes closer to the sun at certain points in the year, and it's further away at other points. That center, yeah, it'd be interesting to find, but there's absolutely nothing there in space. So yeah, don't even bother with that. Okay. The eccentricity of Earth's orbit is actually 0.0167. It's so close to being a circle. Um, yeah, maybe it's understandable to think that why they made that mistake. But thanks to Herr Kepler, he was the one able to prove no, it's not a circle, it's an ellipse. And then the calculations got so much easier. Well, wait a minute, it's not a circle. God's creation has to be made of perfect spheres. And again, he was branded as a heretic for that. Can you believe this? Um, we actually go around the sun at a faster rate in the winter than we do during the summer because of the forces of gravity. The closer you are to that focal point, the faster you're going to go. You get slingshotted around it there, basically. Yeah, 10 more heads exploded. We don't have to worry too much about speed at this point in time. We'll save that for some other day. Okay, so this is a lot. Again, go back, rewind, review as much of that as you need to here. Make sure that you understand how to find major axis, minor axis, find the locations, find the coordinates for both foci, find points on the graph, whether it's a circle or an ellipse, find the center for either circle or ellipse. And we'll talk about it next time.